So last class we learned about membrane potential and resting membrane potential. So membrane potential is the potential difference between the interior and outside of the cell, and resting membrane potential is the membrane potential at rest. And we also learned that potassium is the main driving force of this. Sodium potassium pump plays a huge role in the development and maintenance of the resting membrane potential. The resting membrane potential can theoretically be calculated by the Nernst equation and more accurately by the Goldman constant field equation, and it can be explained by the differential concentration of the ions, differential distribution of the concentration of the ions along the membrane, and the permeability, differential permeability of the ions to the membrane. That is, potassium is more permeable than sodium, and the concentration of potassium inside is much more higher than the concentration of sodium inside. Okay, now knowing that, we will go on to the action potential. Before I start this, I will just tell you that this is a very complicated topic. Both the resting membrane potential, and action potential, these are very complicated topics. I am just telling you the very basics of the topic so that you get a basic understanding of it. Okay, now let's go on to action potential. What you need to know is that when you give a stimulus, all cells do not develop action potential. Only those cells which are excitable can develop action potential. So all cells have resting membrane potential, have a membrane potential, have a resting membrane potential, but all cells do not develop action potential. Okay. Before going on to action potential, we need to know a few terms. That is, what is polarized cell, what is polarized membrane, what is depolarization, what is hyperpolarization, and what is repolarization. So polarized. See, we learnt that the inside of the membrane is negative and the outside is positive. We have seen this experimentally also. Okay, so inside is negative, outside is positive. This is known as the polarized cell, where the inside is negative. What is depolarized cell? Depolarized cell, the inside becomes positive and the outside becomes negative. So, reversal of polarity. In depolarization, there is reversal of polarity. So the inside becomes positive and the outside becomes negative. In hyperpolarization, what happens? The inside becomes more negative than the resting state. Okay. So in hyperpolarization, it becomes more negative than RMP. Okay. And what is repolarization? Repolarization is when this depolarized cell returns back to normal resting state. Okay. So repolarization is return back to normal. So you understood in very simple terms, a very simple concept, what is polarized, what is depolarized, what is hyperpolarized, and what is repolarized. Okay. Now we have talked about this earlier. When we give a stimulus to an excitable cell, giving stimulus to any cell would not do. We have to give a stimulus to an excitable cell. What is an excitable cell? Nerve, we are talking about nerves, but other can be muscles, glands, okay, smooth muscles. These are basically skeletal muscles, smooth muscles. Okay, these are excitable cells. So when we give a stimulus to the excitable cell, we get a electrotonic potential. We'll discuss this. Then we get a local response. This electrotonic potential gives rise to a local response. The strength of this local response depends upon the strength of the stimulus. We will discuss this again. And if the local response developed is strong enough, we get an action potential. Okay, so immediately giving a stimulus does not produce an action potential in an excitable cell. It has to follow some criteria. fulfill some criteria. So what is action potential? Action potential is the sequential change in membrane potential due to opening and closure of various ion channels and its propagation along excitable tissue in undiminished intensity. Each word is important. Okay, so sequential change in membrane potential. This occurs due to opening and closing of ion channels. This is important. Sequential change in membrane potential. Second point important, due to opening and closing of ion channels. Next important, and its propagation along membrane. That is, action potential has to be propagated to be called an action potential. And it has to be propagated in undiminished intensity. So every word is important. Action potential is the sequential change in membrane potential due to opening and closing of ion channels and the propagation of and its propagation along the membrane in undiminished intensity. Okay, so this is action potential. Okay, so before going on to the description and the ionic basis of action potential, we need to know about the stimulus. When a stimulus is applied to an excitable cell, that will lead to production of action potential if the stimulus is of threshold intensity. Okay, so stimulus is the trigger for development of action potential. Okay, for under stimulus we will study threshold stimulus, sub and supra threshold stimulus, all or none law, what is Riobase, what is utilization time, what is Chronaxy, what is strength duration curve, and what is adaptation. Okay, so what is a stimulus basically? Stimulus is any agent which can cause changes in the membrane to give rise to an electrical response. So basically, what is the normal position? What is the normal state? The normal state of the membrane is polarized. Okay, so normal membrane is polarized. Now, any agent which causes this change in polarization, maybe depolarization or hyperpolarization. Depolarization or hyperpolarization is known as a stimulus. The stimulus can be electrical, chemical, or physical, but for all experimental purposes and for even our discussion here, we will consider electrical stimulus. Okay, and this electrical stimulus is mainly in the form of Faraday current. Threshold stimulus. Threshold stimulus is the minimum amount of stimulus strength for a given duration which can produce an action potential in an excitable cell. Okay, before going on to this, we have to remember that the stimulus has to be given to an excitable cell to elicit an electrical response. Okay, so it cannot be just given to any cell and we'll get an electrical response. That it doesn't work that way. We have to give the stimulus to an excitable cell. Here we are talking about the nerve, as I have mentioned earlier. So what is threshold stimulus? Threshold stimulus is the minimum intensity of stimulus for a given duration which can produce an action potential in an excitable tissue or cell. So it is the minimum strength for a given duration. Okay. Now, what is subthreshold stimulus? A stimuli weaker than the threshold is known as a subthreshold stimulus, and a stimuli greater than the threshold is known as a supra-threshold stimulus. Okay. So from the definition itself, we can say that a sub-threshold stimulus will not give rise to an action potential. Only when the stimulus strength is of threshold value, then only we will get an action potential. When the stimulus strength is below the threshold, that is sub-threshold stimulus, we would not get a action potential. We will get some electrical changes, like we have talked about earlier, electrotonic changes and local response, but we won't get an action potential. Unless threshold stimulus is given or stimulus of threshold strength is given, we will not get an action potential. Okay, so sub-threshold and supra-threshold. Sub-threshold will not produce an action potential but will give rise to a local response or electrotonic response. And a supra-threshold stimulus, from the definition, what does it mean? It means a stimulus strength more than the threshold. Okay, so of course it will produce an AP. This will produce an AP. But if we keep on increasing the stimulus above the threshold, the magnitude of AP will not change. Okay, so what does it mean? The AP, the supra-threshold stimulus will produce an AP, but this AP will not be any different from the action potential produced by a threshold stimulus. No matter how much we increase the strength of the stimulus beyond the threshold stimulus, the action potential remains the same. So this is basically the all or none law. Okay, what does the all or none law say? Once the intensity of stimulus has reached the threshold, the amplitude of action potential will remain the same irrespective of increase in intensity of stimulus. Okay, so the stimulus we will get in sub-threshold stimulus we won't get an AP, action potential. For threshold stimulus we will get an action potential of a certain magnitude. Of supra-threshold stimulus we will get the same AP of the previous magnitude. Okay, so increasing the threshold stimulus to a supra-threshold stimulus will not change the magnitude of AP. This is known as the all or none law. Action potential fails to occur if the stimulus is of sub-threshold intensity and it occurs with constant amplitude and form regardless of the strength of the stimulus if the stimulus is at or above the threshold. Okay, so this is the all or none law. Repeating it, action potential fails to occur if the stimulus is of sub-threshold intensity and it occurs with constant amplitude and form regardless of the strength of the stimulus if the stimulus is at or above threshold. Okay? Above the threshold, no matter how much we increase the intensity, the amplitude remains the same. So whether we get threshold stimulus or a supra-threshold stimulus, the amplitude of the action potential will remain the same. For more excitable tissue, less strength of stimulus is required. For less excitable tissue, more strength of the stimulus is required. Okay? Now coming on to Rehoboth. What is Rehoboth? Rehoboth, chronaxy and utilization time are important concepts. What is Rehoboth? Rehoboth is the minimum strength of stimulus which can stimulate an excitable cell. Current less than Rehoboth can never stimulate a tissue. Okay? Similarly, as current less than threshold stimulus can never produce an action potential, current less than Rehoboth can never produce an electrical response. Okay? Sub-threshold can produce an electrical response, but sub-threshold cannot produce an AP. For action potential, we need a threshold stimulus. So how do you differentiate it from Rheobase? Even this, if the current is less than Rheobase, no electrical response will occur. That is, no electrotronic movement, no local response, let alone AP. No electrical movement, electrical change will occur. So, minimum strength of stimulus which can stimulate an excitable tissue is known as Rheobase. You understood the difference between Rheobase and threshold stimulus? Threshold stimulus is for AP, while the Rheobase is for any electrical stimulus, any electrical change, sorry. Now, what is utilization time? Utilization time is the time required by Rheobase to stimulate a tissue. Okay, so utilization time is the minimum time required by the minimum strength to stimulate a tissue. Sorry, let me repeat this again. Utilization time is basically the time required by Rheobase to stimulate a tissue, or time required by minimum strength to stimulate the tissue. Okay, and what is chronaxy? Chronaxy is the time required by stimulus double the strength of Rheobase to stimulate a tissue. Okay, so chronaxy and utilization time are both units of time, measurement of time. Okay, utilization time is the time required by Rheobase to excite the tissue or stimulate the tissue, while chronaxy is the time required by double the Rheobase to stimulate the tissue. This chronaxy is basically the measure of excitability of an excitable cell. The more excitable a cell, the less time it is required to stimulate it. Okay, now let's go on to the strength duration curve. This is based on the concept that the strength into duration is constant. Here in this curve, we are plotting the strength of a stimuli in the y-axis and the duration or the time required by that stimuli to excite a cell in the x-axis. So basically, this curve is obtained by plotting the strength of different stimulus against the time required by them to excite a cell. From this curve, we get that minimum strength of current is required for stimulation. Below this, no stimulation will occur no matter how long the duration. And minimum time must elapse before stimulation can occur no matter how strong the current. See, because the extreme edges are parallel. They never meet the axis. Therefore, a minimum strength is required to produce a excitement of the cell, and a minimum time is required to produce an excitement of the cell. These curves never meet. There is always a minimum strength required and a minimum duration required. Okay, so minimum strength is required for stimulation. Below this minimum strength, no stimulation will occur no matter how long for the duration, as we have talked earlier. So we are seeing the same thing in the curve. This is parallel. This curve is parallel to the axis, so they never meet. So the minimum strength is required. No matter how long the duration is, a minimum strength will be required. Similarly, a minimum time must elapse before stimulation can occur no matter how strong the current. This range, that is between this minimum strength and minimum time range, the strength is inversely proportional to the duration required for that strength to stimulate a cell. Okay, so basically strength into duration is constant. Within this range, strength and duration are inversely proportional. So what does this mean? A stronger stimuli will require less time to excite a cell, and a weaker stimuli will require more time to excite a cell. Okay, strength into duration is equal to constant. Now, so we see that for a threshold stimuli, not only the strength but also the duration is important. Both these factors, the strength and the duration, is important for the threshold stimuli. So on this strength and duration curve, we can also see the Rheobase, the utilization time, and the Chronaxy. So what was Rheobase? Rheobase was the minimum strength which can elicit an electrical response. What was utilization time? Utilization time was the time required by Rheobase to stimulate a excitable tissue. Okay. And Chronaxy was the time, this is on the time scale, this is the time scale, the time required by double the Rheobase. This is Rheobase, this is double the Rheobase. So the time taken by double the Rheobase to elicit a electrical response. Okay, so from here we can see that more the strength, lesser is the time required to elicit a response. But since these are parallel, a minimum amount of strength, a minimum time will be required to elicit a response, no matter how much you increase the strength. You keep on increasing the strength, this won't meet the y-axis. So a minimum time is required. Similarly here, no matter how much you increase the time, these time will not meet this x-axis. Okay, so a minimum strength will always be required. Okay, so this was the strength and duration curve. Now finally we'll talk a little bit about accommodation. What happens if an appropriate strength current is applied? That is, if a threshold current is applied, we normally get action potential. But if this threshold current is applied over a very long time, we do not get an AP. We do not get an action potential. Why does this happen? Because normally action potential develops due to explosive entry of sodium. This explosive entry overwhelms the potassium efflux. But if this stimulus is given over a very long time, this explosive entry will not occur. And thus, this will not overwhelm the efflux, potassium efflux. So, the sodium entry and the potassium efflux will cancel each other out and we won't get an action potential. Okay, so even if the current is threshold, if it is applied over a very long time, we will not get an action potential. Okay, now let's go on to the action potential proper. That is the definition, description, and the ionic basis of the action potential. What is action potential basically? It is basically a sequential change in the membrane potential after application of a threshold stimulus. And it will be propagated in an undiminished manner through the membrane in all directions. Okay, so sequential change in membrane potential after application of a threshold stimulus is called action potential. I've already talked about what are the important points. Just refer to the previous portion of the class. Okay, now it basically starts from the point of stimulus and moves, that is propagated along the membrane at a constant speed and amplitude as long as the other conditions, that is the ionic concentration and temperature, remain the same. So you apply a threshold stimulus, you apply a threshold stimulus, you get sequential change in membrane potential, and this is propagated along the membrane in undiminished intensity and speed, provided the Other parameters remains normal, remains constant. Okay, so what are the other parameters? The other parameters will be the ionic concentration and the temperature mainly. Okay, so these is generally recorded by a CRO, cathode ray oscilloscope. We have already talked about this. Here, one electrode is placed inside the cell and another electrode is placed on the outer surface of the membrane. So this is a representation, graphical representation of the action potential. So this is minus 70 millivolt, minus 55 millivolt, 0 millivolt, plus 35 millivolt. Let me just tell you what are the parts and then I'll explain what these represent. Okay, so we give a stimulus. After a brief period, which is known as the latent period, the membrane potential starts changing. It changes slowly till it reaches the firing potential. Now, after the firing potential is reached, there is rapid depolarization. Okay, so rapid change in the charge. Rapid change in the charge towards positivity. So this was minus 55 millivolt. The membrane potential starts becoming more positive. It crosses 0 millivolt and then overshoots. So the positive overshoot to reach up to plus 35 millivolt. This part is known as depolarizing upstroke. As you know, depolarizing means the inner membrane becomes positive. So you see it is becoming positive, plus 35. Then after it reaches the plus 35 millivolt, it starts becoming negative again. That is, the polarity is reversed. The membrane potential then moves towards the negative side. Okay. Up till 0 millivolt, it is known as a rapid repolarization. From there is a slower process which is called after depolarization till the RMP is reached, that is minus 70 millivolt. Even though the RMP is reached, there is some negative overshoot. This is known as after hyperpolarization. And then finally, the membrane potential returns to the resting level, that is the minus 70 millivolt. So the paths are the latent period, the firing potential, the depolarizing upstroke, the spike, the rapid repolarization, the after depolarization, and the after hyperpolarization. Now, before going on to the ionic basis of these changes, of these phases, we need to know a little bit about the ion channels. You've already done the basics of the ion channels. We are concerned about the sodium and potassium ion channels here, and you have done those in just a few days ago. You have done those. Okay. So just a recap. What are ion channels? Ion channels are basically membrane proteins which allow movement of ions across the cell membrane. These ions cannot cross the membrane on their own, so the ion channels form pores through which the membrane allow the passage of these ions. Okay, so these are basically membrane proteins. Ion channels are membrane proteins. We are concerned about the sodium and potassium, and the sodium channels which we are concerned about here are the voltage gated channels and the ligand gated channels. Mainly the sodium channel are mainly voltage gated and ligand gated. Here we are concerned about the voltage gated channels. Now a little bit about the activation and inactivation. Let's talk about the activation and inactivation of the sodium channels. The sodium channels basically have two gates and three states. Two gates are activation gate and the inactivation gate. Okay. So a sodium channel has an activation gate and an inactivation gate, and it has three states: resting or closed state, an open state, and an inactive state. Okay. At minus 70 millivolt of membrane potential, that is at rest at RMP, the activation gate is closed, but the inactivation gate is open. Okay. So activation gate closed, inactivation gate open, no ion can pass through this. Now, when the membrane potential reaches minus 55 millivolt, what did we just learn? That the minus 55 millivolt is basically the firing potential or threshold potential. Here, the activation gates open and the inactivation gate was already open, so sodium can pass through this and the sodium permeability increases. Now, when the membrane potential reaches plus 35 millivolt, that is after the rapid depolarization, after the fast upstroke of depolarization, what happens when the membrane potential reaches plus 35 millivolt? The activation gate remains open, but the inactivation gate is closed. Okay, and no ion can pass through this. Okay, so this inactive state is basically a refractory state, and this does not respond to any stimuli. So, see, rest, no ion can pass, open, ion can pass, and inactive, no ion can pass. So what is the difference between the rest state and the inactive state? In rest state, the activation is closed and the inactivation is open, and this can respond to stimuli. While for inactive state, the active gate is open but the inactive gate is closed. Inactivation gate is closed. This does not respond to any other stimuli. Okay, so what happens? What is activation here? At minus 70 millivolt, the gate is at rest. As the potential becomes more positive, that is, goes away from the RMP, a stage is reached which is generally minus 55 millivolt, where a sudden conformational change occurs leading to opening of the gate. And thus, the sodium permeability increases and leads to depolarization. So, at threshold potential, what happens? There is a sudden conformational change, opening of A gate, permeability of sodium increases, and depolarization occurs. Okay, we already know what is depolarization. Depolarization is when the inside of the membrane becomes positive. Okay, inside of the membrane becomes positive and the outside is negative. This is depolarization. Okay, so this is how activation occurs. This is how activation occurs. Now let's go to inactivation. Inactivation may be of two types. First, it can be time dependent, and second, it is voltage dependent. Okay, we are talking about the voltage gated ion channels, voltage gated sodium ion channels here, not the ligand gated, only the voltage gated ion channels. These voltage gated ion channels, when the voltage changes, there is conformational change leading to opening of the activation gate. That is, voltage change leads to activation. Now, what about inactivation? The voltage change causes an activation. This voltage change can also cause inactivation. And inactivation can also occur by a time dependent manner. That is, the channel becomes inactivated after a certain period of time automatically, irrespective of the voltage. Some of the sodium channels close or become inactivated after a certain period of time. Now let's go into voltage dependent. What happens? The same voltage change which caused sudden conformational change and opening of the A gate will lead to closing of the I gate. So voltage change will cause closing of I gate. But this is a very slow process. Voltage change occurs, there is opening of opening of A gate. Now there is immediate opening of A gate, but the I gate slowly starts closing. Okay, so a point is reached where the A gate is open and the I gate has not yet closed. So what is happening? Excuse me. The A gate is open and the I gate has not yet closed because it is very slow. At this stage, sodium passes through the channel. So sodium permeability increases during this phase. Now, after some time, the I gate closes. Okay, this slow closure of I gate. Now what happens? The sodium channel is inactivated. Here when the I gate closes, the A gate remains open. So A gate remains open, but the I gate has closed. A gate remains open, opens and then remains open due to a voltage change. This I gate closes also due to that voltage change. So the sodium channel is inactivated. This is refractory and no stimulus can affect this inactivated state. So refractory state, that is, does not get stimulated. Now this continues till the RMP is minus 70 millivolts. So as soon as the MP reaches minus 70 millivolt, there is a conformational change in the gates. Now the A gate closes and I gate remains open. That is, I gate opens. The A gate closes and the I gate opens. So this is the closed. Sorry about the out of focus camera. Okay, when I'm writing, the camera becomes out of focus. So this is the closed state or the rest state, and this is found in when the MP is about minus 70 millivolt. Okay, so this was all about the opening and closing of the ion channels, of the sodium ion channels. Opening and closing of sodium channels is affected by calcium. Okay, so there is affected, opening and closing is affected by serum calcium levels. If there is increased calcium, the threshold of opening increases. Therefore, the membrane becomes less excitable. What does this mean? If the threshold increases, more stimulus will be required to more stimulus strength will be required to reach the firing level, and thus the membrane becomes less excitable. Okay, less readily reacting to the stimulus. Now if there is less calcium, what will happen? The threshold will decrease. That is, the membrane will more easily become stimulated. That is, the membrane becomes more excitable. Okay, so this can explain that in hypocalcemia we get tetany. You learn this later, just know the terms. In hypocalcemia you get tetany. What is tetany? This is increased tendency of contraction of muscles, of certain groups of muscles. So in hypocalcemia, what is happening? When calcium decreases, the threshold decreases, so the membrane excitability increases. So with only small strength of stimulus, the membrane action potentials are generated and muscle contraction occurs. So in hypocalcemia, you get tetany. In hypocalcemia, you get increased contraction of muscles. Okay, you don't need to know in much more details now. You will be taught about this later. Now let's go on to the potassium channels. You have already done the major part of the potassium channel. I'm just going to talk about the activation. Now, the potassium channel can be of various types: calcium activated, leaky potassium channels, voltage gated channels. These will be important later. This is out of the purview of this class. Now, leaky channels, these are important for RMP generation. I've already taught that the RMP, that the potassium efflux occurs due to the concentration gradient. This is through the leaky channels. Okay. Now, voltage gated channels. These are important for AP generation. Basically, during AP generation, these channels are always active, but the sodium overcomes or overwhelms these potassium channels. After some time, the voltage gated potassium channel comes into play. So, how it is activated? You need to know how potassium channel is activated. In the resting state, the activation gate is closed. Now, when the membrane potential starts changing towards zero, what will happen? The gate will start opening. What happened when the membrane potential was changing towards zero from minus 55 millivolt? The sodium channels were opening. The potassium channels were also starting to open, but it is a very slow process. By the time they manage to open, what happens? The sodium channels have already started closing. So, if the sodium channels have already started closing, the sodium influx decreases and the potassium channels are now open, so potassium efflux increases. As a result, the depolarization stops, that is, the entry of positive charge decreases, the exit of positive charge increases. So the depolarization stops and the rapid repolarization starts. This goes on to rapid repolarization, then delayed repolarization, and then finally we get this hyperpolarization where the membrane potential, wait a sec, let me take you to the diagram. So you see, at this point, the sodium channels close and the potassium channel starts opening. That will lead to stoppage of depolarization and start of rapid repolarization, then after depolarization, and then finally after hyperpolarization. This occurs, that is, the potassium channels remain open for a long time. Therefore, even if the membrane reaches the resting level, that is the RMP level, there is some negative undershoot. Okay, this is due to delayed closure of the potassium channels. They open slow, they close slow. Okay. So after they close, the membrane potential returns to the resting value. Now let's go on to the ionic basis of action potential. Okay, we have a little bit of knowledge about the potassium channels and the sodium channels, which are very important for understanding the ionic basis. So we have already done this. A stimulus is given. We get a latent phase. The membrane potential starts changing, that is, it becoming less negative and more positive, moving away from the RMP. This movement occurs very slowly till the firing potential is reached. Here, firing potential is minus 55 millivolt. Once the firing threshold is reached, depolarization occurs. So this is the upstroke depolarization, rapid upstroke depolarization. It crosses the zero mark, then overshoots to plus 35 millivolt, forms the spike, comes down rapidly, very rapidly, that is, rapid repolarization occurs up till the zero level. Then after that, there is slow movement of the membrane potential towards the resting membrane potential, that is, the membrane potential becomes more negative. This part, this 0 millivolt to minus 70 millivolt is basically known as after depolarization, and then finally, due to continuously open potassium channels, this membrane potential becomes even more negative than the RMP. and finally this is known as after hyperpolarization, and then finally it reaches the resting membrane potential level again. So this was the electrical event. Let's look at the ions. This orange mark is the sodium ion, and this blue mark is the potassium ion. So this shows the permeability change of the sodium and potassium ions in different phases. So sodium, on giving the stimulus, the sodium channels slowly start opening until threshold is reached where there is opening of a massive number of sodium channels because of the conformational change leading to opening of the activation gate. So massive number of sodium channels open. There is explosive entry of sodium leading to depolarization. The spike potential formed, plus 35 is reached. The voltage gated sodium channels start closing. Now the slow potassium channels open. The sodium channels are inactivated. The potassium channels remain open. So potassium channels remain open in rapid repolarization, in after depolarization, in after hyperpolarization. In after hyperpolarization, now the sodium channels move from inactivated state to closed state. Finally, the sodium and potassium channels both remain closed when the membrane potential returns to the resting value. Okay, so the permeability of sodium increases, then decreases. There is slow increase in permeability of potassium. So spike increase in permeability of sodium and slow increase in permeability of potassium. Slow increase and slow decrease for potassium, and fast increase and fast decrease for sodium. So what happens? In the latent phase, both the channels are closed, the sodium potassium channel. In firing threshold phase, the sodium channel starts opening. In the rapid upstroke depolarization state, massive number of sodium channels open. Then rapid repolarization, the sodium channels close and become inactivated. Potassium channels are finally open. And after depolarization, the sodium channels remain inactivated. The potassium channels remain open. After hyperpolarization, the potassium channels start closing, while the sodium channels move from the inactivated state to the closed state. This resetting is triggered by conformational change due to the change in voltage. Now, when the membrane potential returns to the resting level, both the channels are closed. Okay, so this was the ion channels and ions in brief. Now I will discuss this in details. Now let's go on to the ionic description of the ionic basis of action potential. So what happens in resting state? For sodium, the concentration and the electrical gradient of sodium is directed inwards. Both the concentration gradient and the electrical gradient is directed inwards. So sodium wants to move into the cell, but it cannot move into the cell because the sodium channels are closed at rest. But for potassium, what is happening? The concentration gradient is directed outwards and the electrical gradient is directed inwards. Now, the leaky channels of potassium are always open. So these leaky channels allow the movement of potassium in and out of the cell. When these two forces, the chemical and the electrical force, becomes equal, there is no net movement of potassium through the leaky channels. Okay, this way resting membrane potential is produced, as you have seen earlier. Okay, so at rest, this is the situation. At rest, no potassium movement occurs through the leaky channels because these two, the electrical and the chemical gradient directed in opposite directions, become equal. Now, as the membrane becomes more positive, that is less negative, this electrical gradient, electrical force decreases. Okay, so this, as it becomes less negative, the inward electrical force decreases and potassium efflux occurs through the leaky channel. Okay, so at rest, no potassium movement. At rest, there is no sodium movement because the channels are closed. At rest, there is no potassium movement because through the leaky channels are only very little potassium movement because these concentration gradient and electrical gradient cancel each other out. Now, when the membrane potential starts becoming less negative due to a stimulus, that is when membrane starts getting depolarized, the inward electrical force decreases. That is this one, electrical gradient decreases. As a result, potassium efflux occurs through the leaky channels. Okay. But in case of the action potential development, this potassium efflux through the leaky channels is not of much importance because the sodium influx overwhelms this potassium efflux. Okay, so now let's go on to see what happens when we give a depolarizing stimulus. We apply a stimulus which is basically a depolarizing current. What is a depolarizing current? Depolarizing current changes the inner membrane from negative to positive and the outer membrane from positive to negative. So we give a depolarizing stimulus. After some time passes after giving the stimulus, this is known as latent period. After the latent period, all the changes start. Okay, this latent period basically depends upon the distance of the recording electrode, the stimulating electrode and the recording electrode, and it also depends upon the velocity of conduction of the impulse. Okay, so we give a stimulus, then we get a latent period. After that, the membrane potential starts changing. It becomes less negative, that is more positive, and moves away from the RMP. That is, the RMP was minus 70 millivolt. Now the membrane potential starts changing, becoming less negative. Okay, due to this change in voltage, that is the membrane potential becoming more positive or less negative, the voltage gated sodium channels start opening. Not all of the sodium channels open. Some of the sodium channels start opening in response to this voltage change. Now, due to this opening of voltage gated sodium channels, the sodium permeability increases and some sodium moves into the cell. Now, as positively charged sodium is moving into the cell, the membrane potential becomes even more positive. That is, the membrane potential starts becoming depolarized. So, more voltage change, again more sodium channels are opening. So, a positive feedback loop is set up. Okay, so do you understand what is happening? As the voltage and due to the stimulus, the voltage changes, becomes more positive. As a result, sodium channels open, some sodium channels open, sodium enters, the membrane becomes even more positive. As a result of that, even more sodium channels open, and we get more positivity of the membrane and further sodium channel opening due to the positive feedback. So let's see what is the positive feedback control of the sodium channel. Okay, see, this is the positive feedback loop, which says that influx of sodium stimulates further opening of the sodium channels. we give a depolarizing stimulus. As a result of that, we get opening of the voltage gated sodium channels. This increases the permeability of sodium. As a result, there is increased flow of sodium into the cell. That leads to depolarization of the membrane. That is, the membrane becomes less negative or becomes more positive, whichever you prefer. As a result of this, there is more opening of the voltage gated sodium channels. Okay, this depolarization stimulates more opening of the voltage gated sodium channels, and then again this cycle is followed. So this is a positive feedback. Opening of sodium channels causes more opening of sodium channels due to change in the membrane potential. This feedback cycle only stops when there is inactivation of the sodium channel. So we have talked about time dependent and voltage dependent inactivation. Positive feedback is stopped when there is time dependent or voltage dependent inactivation of the sodium channels. So by this positive feedback mechanism, more and more sodium channels keep on opening, and as a result the membrane becomes more and more positive. Now a point is reached where the membrane reaches the firing potential, which, as we have seen, was about minus 55 millivolt for a nerve cell. So initially it was minus 70 due to this positive feed stimulus, and then this positive feedback, the membrane potential goes from minus 70 millivolt to minus 55 millivolt. That is, it becomes more positive. At this firing threshold or at this firing potential or threshold potential, the maximum number of sodium channels are open. Okay. Due to this maximum opening of sodium channels, there is explosive entry of sodium into the cell. All the channels are open, therefore a large number of sodium enters the cell. And due to this, rapid depolarization occurs, followed by overshoot. Okay, so what is that? Due to explosive entry of sodium, the interior becomes very positive. From minus 55 it reaches 0, then from 0 it reaches plus 35. So there is a rapid depolarization and a positive overshoot. Okay, this is due to explosive entry of sodium. So what is the cause of the depolarization? The cause of the depolarization, this rapid depolarization, is basically sodium entry into the cell along its concentration and electrical gradient through the large number of open sodium channels. Okay, you understood what happens when you give a stimulus? In what direction the membrane potential changes? Then how a positive feedback loop is set up, and finally how we get this rapid depolarization and overshoot. So we understood why we get the latent period, how we reach the firing potential, then why we get the rapid depolarization upstroke. Now another thing of consideration is that the Nernst potential of sodium is plus 65 millivolt. So that should mean that sodium will pull the membrane potential to plus 65. That is, the flow of sodium will stop only when the membrane potential reaches 65 millivolt, plus 65 millivolt. But by experiment we see that sodium entry stops at plus 35 millivolt. Why does this occur? This occurs because due to inflow of sodium into the cell, the concentration gradient decreases. Okay. What about the electrical gradient? The electrical gradient is reversed. Initially inside was negative, outside was positive. But now the inside is positive, outside was negative. So sodium was moving in along its concentration gradient and electrical gradient. The concentration gradient decreases, the electrical gradient is reversed. There is also some time dependent closure of the sodium channels. some time has passed, and irrespective of the voltage, the sum of the channels close. And finally, by this time, the potassium efflux has started. So, potassium efflux, and that means positive ions have positively charged sodium ions movement into the cell is slowing down, and movement of positively charged potassium ions out of the cell is increasing. So the membrane potential does not reach plus 65 millivolt, it stops at plus 35 millivolt. Okay, now let's go on to the repolarization part. Up till here, the depolarization is complete.